So for announcements, first thing I want to say is that we are now officially into Q4. So Q3 grades, I believe you guys will be able to see those by Friday. Do not quote me 100% on that. I believe it's Friday. I'm not 100% sure on that. Okay. Speaking of Q3 grades, what you do see on Skyward will most likely be what you see on your report card, except for those of us who do have to make up tests and quiz. So if you were not present on Friday, did not take our test, I will be staying after today so that you can make that up, so it will appear on your report card. Okay, if you do not have the time to stay after school today, you can also stay after tomorrow. I just cannot say that it'll be on the report card. Okay. So for those of us who have to make up our test from Friday, we can stay after today if we want to see it on our report card. Otherwise, you can make it up to tomorrow during my sport time after school. I just can't say that it'll be on the report card for sure. Okay. Other than that, a reminder that next week, next Tuesday, for those of us who are hybrid, a reminder that we will start our 4-day-a-week schedule. So all of those of us who are hybrid will be coming in all 4 days of the week starting next week. Okay. Does anybody have any questions? Okay. So a reminder, if you haven't done so already, to go to our Pear Deck for today. What we'll be doing today and tomorrow is reviewing our periodic table. So a reminder, this is how we keep track of participation in class. So this will be our participation points. All right. So for this first slide, what I want you guys to do is an organizing activity. So there should be 5 shapes, 3 circles of different colors, and 2 triangles of different colors. What I would like you guys to do is organize the shapes in a way that makes sense to you. There is no correct answer for this. This is just how you guys want to organize it. Okay, and I'll give you guys until about 9:20 to do that. So a reminder for those of us who have not done so already to get to our Pear Deck, you hit that current lesson button, hit that link, or you can hit modules, scroll all the way down, hit 316, periodic table review. So for this activity, does anybody want to share why they organized the shapes the way they did? A red circle, blue circle, green triangle, and a blue triangle. All right, so Mark said he organized the circle triangle pattern. Which I can see. Anybody else do it differently other than the circle triangles? Did anybody focus on color before they focused on shape? Yes, no, maybe so? Yeah, so someone did focus on color before shape. Yeah, the color of a rainbow just followed what color was next. So you can see that a lot of people organized it in different ways. Okay. So an example of that, for me, how I would do it, is that I have my shapes. So for me, I would go alphabetical. So I put C above T. And then I also have colors. So I have blue, green, and red. So I'm going to go alphabetical based on colors too. So for me, and this does not have to apply to you guys, I start with my blue circle, with my blue triangle underneath. I have my green circle with my green triangle. And then lastly, I have my red circle. And this is just how I would organize it, just because I want to go alphabetical with my items. So like you guys had done, you guys can focus on circles and triangles. You guys can focus on colors. You can even do it based on the rainbow, starting with, I believe it would be red, green, and then blue. So opposite direction of what I get. All are great ways to organize these shapes. So other than these shapes, what else do we organize? What other things are there that we organize? So what other things do we organize? Yeah, we organize clothes. You organize your room. When I was in school, I had my subjects color coordinated by folder. Anything else? What else do we have to organize? Okay, so clothes and room are great examples. So let's talk about why we're even talking about organization in the first place in a science class. So when we talk about organizing, there's something that we deal with heavily in chemistry that was organized specifically based on properties, and that would be our periodic table. So what we're going to do is we're going to watch a short little video explaining the periodic table a little bit. And then just so you guys are aware that this is a video made in the UK, so their element boxes are going to look a little different. So instead of like decimal places for our mass numbers, they use commas. Okay, so those are not like 30,000 or something like that. It's 30 point. It's just they use commas instead. Okay, so let's watch this video.
The truly periodic table. The periodic table is this chart with a strange shape, with letters and numbers, neither a square nor a rectangle, with such a characteristic shape. Unmistakable. Some people know what each of these letters represent. C is the chemical symbol for carbon. O is the chemical symbol for oxygen. The chemical symbol for iron is Fe. Zn is zinc. There are even those who know the chemical symbol for sodium is Na, because it comes from the Latin natrium. Or that the chemical symbol for gold is Au, because in Latin it was called porous. And also some know the meaning of the numbers that appear next to the letters, like, for example, the atomic number, which is the number of positive and negative charges of the atom. But what exactly is the periodic table? The periodic table is a chart that represents all 118 chemical elements that constitute the known universe. Everything around us is made up of at least one of these elements. 94 of these elements can be found in nature. The rest were obtained in laboratories. 118 elements may seem too little for an entire universe, but it's not. Let's see. In stars like the sun, 94% of all the atoms are hydrogen. The human body itself is very scarce on chemical elements. For every 100 kilos of weight, 65 kilos are oxygen atoms, 18 kilos are carbon atoms, and 10 kilos are hydrogen atoms, which leaves little room for all the other essential elements. Nitrogen, calcium, phosphorus, potassium, sulfur, chlorine, sodium, magnesium, iron, cobalt, copper, zinc, iodine, selenium, fluorine. The wonder of the chemical elements is that they combine with each other. There's an almost infinite number of possible combinations that produce all the different chemical compounds needed to keep us alive and build everything around us. The water we drink, obtained by combining an oxygen atom and 2 hydrogen atoms. The glass we drink it from. The sugar in our coffee. Coffee. The cup and the metal of the little spoon we stir it with. The plastic our computer is made of. The rubber on the tires of our car and the gasoline that makes it run. Proteins. DNA. Everything around us and inside us are atoms that combine. An atom is the smallest recognized division of a chemical element and consists of a central core. Protons, positive charge, and neutrons, no charge. Surrounded by a cloud of electrons, negative charge. The properties of each chemical element are defined by the atom's nucleus and by the way electrons distribute in layers around it. These properties define the way atoms combine. Or not really. Atoms react with each other through electrons at the last layer, the outermost layer. If the last layer has the same number of electrons, this means that the properties of these atoms are identical. The distribution of the elements in the lines and columns in the periodic table is not random, or just a question of design. The position of an element on the table tells us something about its chemical and material properties. It helps us to know, predict, how 2 elements can combine. The periodic table organizes the elements from smallest to largest, according to its core, the distribution of electrons. In the first column of the table, we have the elements that have a single electron in the outer layer. And in the last column, we have those who have filled this layer. That's why each chemical element in the periodic table has a very well-defined neighborhood. Above, below it, has elements with the same distribution of electrons and very similar properties. And on its right, it has an element that has an electron and 1 proton more, and therefore has different properties. We call it periodic because in this table, the elements become similar again periodically. Let's see, if we start at 3, lithium, the properties will vary regularly along the line until 10, neon. Here, the last layer of electrons gets full, and we move on to the next line and back to the first column. The properties of this element, 11, sodium, are again identical to the element that is directly above it, and so on.
Okay. So that is our video, giving a quick little recap at our periodic table, which again, we will be reviewing today. We're going to talk more specifically about groups and periods and how that deals with our atoms, our models. And then tomorrow, what we're going to do is we're going to review our specific group names and how they behave. Okay. So moving on, we have our elements on our periodic tables. They're arranged 2 ways. So they are arranged vertically into groups. and they are arranged horizontally into periods. So our groups, if you looked at one atom of every element in a group, you would see that each atom has the same number of electrons in its outer orbital / ring. So that means that all of those have the same number of valence electrons, those electrons that we find in that outside ring of our model of the atom. So for an example, the group 2 atoms all have 2 electrons in their outer orbitals. So what we are going to do is we are going to draw on this slide the atom for beryllium, and we are going to compare it with the atom for magnesium, just below it. So for this, let's start off with beryllium. So element Be. For this, I will tell you the number of protons, neutrons, and electrons, okay? So for protons, we have 4. For neutrons, we have 5. Electrons, we have 4. So to start off my atom, I'm going to have my nucleus. Out of protons, neutrons, and electrons, what am I going to find in the nucleus of my atom?
Protons and electrons. I mean neutrons.
Yep, protons and neutrons. So my positive and my no charge particle. So for beryllium, that is 4 and 5. I have 4 electrons to place. So let's start off with my first orbital. How many electrons can go in my first orbital for my atom?
2.
2. So I'm going to draw my 2 electrons. So I need another orbital to fit my remaining 2 electrons. Here are the other 2. So now I have 4 protons, 5 neutrons, and a total of 4 electrons. Notice that it is beryllium. It is in group 2. So all my atoms will have 2 electrons in their outer orbitals. So in my outside orbital or ring for my Bohr's model, I have 2 electrons. Okay. All right. So let's compare that with magnesium. So magnesium is Mg. We have 12 protons, also 12 neutrons, and 12 electrons. So all the same numbers. So again, in my nucleus, what 2 subatomic particles am I going to find?
Protons and neutrons.
And protons and neutrons. This time I have gone down, so I increase an orbital. So I need 1 additional orbital. So for magnesium, I need 3. So again, starting with my first orbital, how many electrons can go in there?
2.
2. Now my second orbital, I have more electrons to fill. How many electrons can my second orbital hold?
8.
8. And a reminder, we go around like a clock for our first 4. So we start at 12, go to 3, 6, and then 9, and then back up to 12 and start pairing. So now I have 10 electrons placed. I am now on my outermost ring. I have 2 electrons left. So having 2 electrons in my outermost ring is exactly what beryllium is. It's just I have gone out an extra orbital. So their outside rings look exactly the same. The only difference between beryllium and magnesium is that magnesium is larger. It contains an extra orbital, so it can hold more electrons. Okay. I will give you guys a minute to finish copying this down. So beryllium, we have in our nucleus 4 protons, 5 neutrons. Our first orbital with 2 electrons, our outside orbital, the second one, with 2 electrons as well. Magnesium, we have 3 orbitals total, with 2 electrons in our first, 8 in our second, and 2 in our outermost or our third orbital. Both beryllium and magnesium are part of group 2, so they will have 2 valence electrons or 2 electrons in their outer orbitals. Hold on 1 second, guys. Okay. All right. So moving on. Our groups, so our number of outer or valence electrons in an atom affects the way an atom bonds. And we'll talk more about that after spring break, but that has to deal with something like this, which this is H2O or our water. So we'll talk about how this happens and why it happens after spring break. So the way an atom bonds determines many properties of an element. This is why elements within a group, so within that row, that column, or in that column, excuse me, in that column have similar characteristics, which we'll talk more about tomorrow. So other than groups, we organize them by periods. If you looked at an atom from each element in a period, so in those rows, you would see that each atom has the same number of electron orbitals, so those rings. An example, we have the period 4 atoms that each have 4 orbitals. So for this, we are going to draw our atom for potassium, which is element K, where we have 19 protons, 20 neutrons, and 19 electrons. We are going to compare that to the next element over, which is calcium, which has 20 protons, also 20 neutrons, and 20 electrons. Okay. So since Both of these are in period 4. How many orbitals will each have?
4.
Yeah, they'll each have 4. So each will have 4 orbitals surrounding their nucleus. Okay. So for potassium, we put in that we have 19 and 20. For calcium, we put in that we have 20 and 20. So filling in our electrons for potassium. For our first orbital, how many electrons can we put in?
2.
2. For our second and third, how many can they hold?
8.
They can hold 8. And then, so far, I have 18 electrons filled in, and I need 19. So for potassium, how many are in this outermost, or the 4th orbital? How many do I need to put in? So I have 18 electrons filled, but I need 19. So how many are left for this outermost?
1.
And 1. Okay. And then calcium, the electrons will look the exact same, except I have 1 additional more. So besides, so the outside ring will be the only thing that looks different. It'll just have that additional electron. So instead of 19, calcium has 20. So both of these are period 4 atoms or elements. So they both have 4 orbitals. Calcium is part of group 2, so that means it'll have 2 valence electrons, while potassium is part of group 1, so it will have only 1 valence electron. Okay. Does anybody still need this up on the board? Okay. So a recap is that our periods tell us our number of orbitals. For example, our period 4, they have 4 orbitals, while our groups tell us our number of valence electrons. So our group 2 elements have 2 valence electrons in their outermost orbital. All right, and then this is a little intro for tomorrow. So each group, those columns, have distinct properties. So the periodic table is divided into several groups based on the properties of different atoms/elements. So these, for tomorrow, we will talk about our groups with specific names. I'm going to turn on the lights, do some recap announcements before ending class today. And then a reminder that I do publish your notes at the end of this. A way to access them is by going on to your email. It'll come to you in a Google Doc form. If you do not get that takeaway, your notes from in class today, please let me know. Okay. All right, so before finishing class today, a reminder about makeup tests and quizzes. I will be here after school today if you would like that to be posted on your report card. Otherwise, you can make the test up tomorrow if you would like. I have my support time after school from 2:40 to 3:10. And we'll use that same link. Okay. All right. So with that, for those of us who are virtual, you guys can stick around if you guys have any questions, but otherwise, you are dismissed for the day. Have a great day, and I will see you guys tomorrow.